This is part 2 of lesson 10.6, the ratio and root test. In this part of the lesson, now that we've gone through all the different tests that are available for determining the convergence of an infinite series, we're going to talk about how do you decide which test to use if you're just asked to determine if a series converges and it doesn't tell you what test you are to use. So we have 10 tests to choose from, and sometimes one test might be better than another. At other times, you could use different tests. So the idea is, though, to pick the most efficient test to get to the solution as quickly as possible so you can move on. So here are some questions to consider. First is the series a special type? Because those are easy. Is it a geometric or p-series, an alternating series, or a telescoping series? Second, can the series be compared to a special one? So then you can use the comparison test or the limit test. Number 3, does the nth term approach 0? If not, then you can say it diverges. You can't say the test that the series converges, but if you're trying to determine if it diverges, the nth term test will be very useful. And then the other one is that, the last question, can you apply the integral test, the ratio test, or the root test? Now the integral test is nice when you have like series that look like well-defined functions that you know are decreasing and bounded, so you can find the integral, the limit of the infinite integral. And of course the ratio and root test that we've talked about in this lesson, they have very nice defined types of series like factorials and nth powers for the ratio test, and of course nth powers for the root test as well. So in this example, number 4, we have 7 different series, and each one of these you could use a specific series test for. So the question is, can you figure out what the best one is? And again, there might be more than one choice for them, but the idea is to be as efficient as possible. So let's start with letter A. So in letter A, what we see is that we have I'm just going to not say the summations. I'm just going to mention the a to the nth, a sub n term. So we have pi over 3 to the nth power. Now you might be tempted to go, oh, I can use the root test, but there's actually a quicker way to do this one. This one is a geometric series. And you can see that your r is going to equal pi over 3. And that is going to be greater than 1. So you can say already that this series diverges without having to take a limit or anything. But I will note here, because it is a pretty simple test to use, that the root test would work too. But it's not as efficient as seeing that series is a geometric series. For letter B, series like this is a good one for the limit comparison test. And the reason why is, if you look at 1 over 4 n plus 1, it would be bounded by the harmonic series. And since the harmonic series diverges, this would diverge as well. So we could say that this series diverges. Because it would be bounded by that divergent series. So you can say very quickly that letter B diverges. For letter C, what we have here is we can use the nth term test, because you can see that that limit, if just by looking at it, is going to be 1/4. So you can say that this series diverges. So this would be the nth term test for divergence. Because you can take the limit as n approaches infinity of n plus 1 over 4n plus 1, and that's going to equal 1/4, which is not equal to 0, so this series diverges. Letter D. Letter D is kind of a strange one. You have n, you have e to the n squared, but if you notice, none of the other tests seem to fit. So my go-to one, especially if it seems like I can integrate something, is the integral test. So letter D is going to be the integral test. Be a little consistent here. So I can let u equal like n squared, and then du equals 2n dn, and do a u substitution and integrate this. And what I'm going to find is that the limit as t approaches infinity of the integral from 1 to t of, I'm just going to put x's here, x over e to the x squared dx with my u substitution is going to equal 1 over 2e, so I can say that it converges. All right, letter E, that one is obvious because of that part. That's an alternating series, so that's going to be an alternating series test. So you can do your 3 checks on that one, and see that a sub n is positive, that a sub n plus 1 is less than a sub n, and that a sub n approaches 0 as n approaches infinity, so the series converges. So let me just write that down real quick. So a sub n is positive, a sub n plus 1 is less than a sub n, and 3 is that a sub n is going to approach 0 as n approaches infinity, so this series converges. Now you'd want to write it a little more formally than that, but I'm just doing that for our discussion here of what test to use. And with the alternating series too, don't forget it might ask if it converges absolutely, that you want to take the limit of the absolute value of a sub n first. Okay, so letter F then. Letter F, hopefully that's kind of obvious because you have the nth power here. So this is a root test. The series is raised to the nth power. So if you take the limit as n approaches infinity of the nth root of n plus 1 over 3n plus 1 to the nth power, and of course that's the absolute value of that, that's going to just equal the limit, the power goes away, of n plus 1 over 3n plus 1, and you can see that's 1/3, which is less than 1, so this converges. That's why that's a nice slick test if you have an nth power. Like I said, you could use it for letter A, but letter A, it's much easier to say that it is a geometric series, especially if it's asking you what its limit is, because then you'd use your S equals A over 1 minus R. And then finally, the last one, as you can see, we have an exponential and a factorial. So that is the perfect setup for the ratio test. Because of especially the factorial. So just doing that real quick. So we have n plus 1 factorial over 3 to the n plus 1, and that's going to be multiplied times the reciprocal of a sub n, and that's going to give me the limit as n approaches infinity of n plus 1 over 3, and I can see that that's going to infinity, so this series diverges. So you can see that if you pick the right test, that the test doesn't take that much effort. The one that takes the most effort, I think, is the integral test, especially because you have more complicated series, so that's why you end up using that test. So that's a good little chart to go by with some different types of series to help you figure out what test to use. So what we have on the last page of our notes is a summary of all the tests of sequences and series and when to use them, how you know whether they converge or not. Also on here is a little bit about error bounding and the remainder. And all of the tests are here with a little summary. The only thing that isn't here is some of the tests, like the integral test and the alternating series test, requires you to make sure that there are conditions met before you use them. So please remember to check those conditions first before you use the test. All right, that concludes our discussion of the root and ratio test and our convergence test.